Ladies and gentlemen, recording has started. So, yesterday, we started on section 5.3 dealing with friction. And yesterday we talked about kinetic friction. The friction acts against a moving object. And, like it says here, right, kinetic friction acts between sliding surfaces. And we talked about then that the nature of friction is that frictional forces resist motion. So, today, just wanted to show you a couple of things on the lab quest, just to kind of bridge the gap between the kinetic friction that we were talking about yesterday, illustrate a couple of the concepts, and then go from there. Okay? So actually, before I do that, want to go here. So the next thing that we did yesterday was we looked at this equation that told us about the actual force of friction that is existing on an object, right? The force of kinetic friction. And we said that the force of kinetic friction is actually determined by two things. The first is the normal force, that friction is proportional to the normal force. However, that doesn't tell us the whole story. We also included this coefficient of friction, right, mu sub k, that tells us about the surfaces that are involved. And like the example that I think I used yesterday in class was, you know, if we're talking about you standing on an ice rink and you standing on the sand at the beach, the normal force that you have in both of those instances is exactly the same. But the amount of friction that you would feel would be different. Not because normal force is different, but because the coefficient is different. Remember, coefficient deals with surfaces. Okay? Good there. And so then to illustrate a couple of these things, let's go here. And so I attached the force sensor to the lab quest. And if you're watching the video, you can't see this, but oh well. So, all right, so here's block. Here's block, and I tie strings to the block. I'm just going to put the block on the table. Motion, or not motion sensor, force sensor. I tie the loop in the string so I can use it to apply force. This measures the force that I am applying in this situation. Okay? So I'm going to start off with the string not pulled, right? Nice and loose, no tension in the string. And then I'm going to start up my data collection. And I'll zoom for you guys here in a second. Right now, that data collection, the force is showing as 0. But if I pull this block across the table at a constant velocity, and I will stop this data collection here in a second. But we can kind of see here, if I zoom in for you guys, even though it's still collecting data, if you can see here, right, the force during that time, fairly consistent, right? And if I stop this, we'll zoom in, and it gets kind of jagged, but remember the scale, right? The scale kind of auto-corrects itself. So here, we're fairly consistent right around 0.5 newtons. Now, that was the force that I was applying to the block, but if we're pulling that block with a constant velocity, we know that the net force has to be 0. So if I'm applying a fairly consistent force of 0.5 newtons, that means that the frictional force has to be a fairly consistent 0.5 newtons. Good there? All right. I'm going to pull this back over to the other side. Start it over there. I'm going to save this data. Okay. And I'm going to start run 2. This time, I'm going to pull the same block, but at a faster constant velocity. Okay? Here we go. And again, here we go. We're starting off. Force fairly consistent around 0. We see some jumping because the scale is a lot smaller here. Okay? But I'm going to pull it at a constant velocity, but a faster constant velocity than I did the first time. Okay? Ready? Here we go. And put that down to 0. stop it here. Okay. So now, let's take a look at both of them together. And if we see right through here, red was trial 1 where I pulled it slowly, blue was trial 2 where I pulled it more quickly. What are we seeing about the amount of friction that both of those things experienced in both cases? Pretty similar, right? Right about the same level on the y-axis. So to sort of summarize these things, actually, one more, okay? So we'll save that. All right, last trial for this part. I'm going to take these two heavy blocks and put them on top of my wooden block, right? More gravitational force now, more weight, right? But in more weight, the response then also more normal force as well. So, we'll start this up. Again, we're right around 0. I'm going to start off, or I'm going to pull at a nice constant velocity, and we'll see what this one looks like. Ready? Here we go. And we'll stop that. Okay. Fairly consistent. I dropped off a little bit because my cord got stuck in the groove between the two tables a little bit at the end. Right? But if we put all three of them up there, right, increasing the normal force on this block has significantly increased the amount of friction that that block experiences. Good there? Okay. So, the last part I'm not going to do, and I'll tell you why in a second, but these demos summarize some of the key points about kinetic friction that you have on page 2 of your packet. So, properties of kinetic friction to sort of wrap up the whole idea of the kinetic friction part. First, it opposes the motion of surfaces, meaning that it goes in the opposite direction of whichever way the two objects are moving. Okay? Second, it is proportional to the normal force between the surfaces. That shows us here by the green being much higher than blue or red. But it's the same regardless of the speed of the surfaces. And that, showing us here, red and blue, where red I pulled quickly and blue I pulled slowly, basically came up with the same amount of friction in both cases. Okay? The last demo I can't do just because of the way... Okay, Christian, go ahead, I'm sorry. Okay. So, that comes from, remember we said that really at its core, friction is an atomic thing, right? Repulsion, attraction between subatomic particles. It's the idea, so the friction force is kind of like, as somebody is running past you, you're trying to grab them, all right? Now, with that analogy, if somebody was running faster, you might think, well, it's harder to grab them, there should be less frictional force. And in our analogy, that would be true. But here, because we're talking about the interaction between those subatomic particles, attraction, repulsion, that stuff adjusts almost instantly. So regardless of how fast those particles are going, or the surfaces are going past each other, that those subatomic particles adjust so that they feel the same resistance from the new part that they did even if it was going slower. Does that make sense? Right? So that's why, because it is that adjustment of the subatomic particles as it goes by, really it doesn't make any difference. Okay. The net force stays at 0 because I keep applying the force, and that causes the subatomic particles in the surfaces to keep adjusting, right? If I stop, right, that friction force goes away because those particles can then rearrange themselves instantly into the lowest possible energy state, or the least objectionable energy state, if you want to think about it that way. But they never move from that state because that's how they've adjusted themselves with the two surfaces in that position so that, you know, the repulsion is the least as possible. Does that make sense? Okay, now, that's a good question, Krista, and hold on to that just for a second because that'll be a good transition into our next part, okay? So you're talking more about the beginning of the motion as opposed to when it's going across the table, okay? Yes, but which constant velocity it is depends on how much acceleration it has at the very beginning, and that's what that'll transition us into the next part. Okay, Brett, go ahead. Yep. Yep. It's more me not pulling anymore. So remember we said that tension forces are the same throughout the entire string that we're talking about, right? So in order for there to be tension in the string, there basically has to be something holding it on both sides. If I let go, tension goes away. If the string breaks on the other side, tension goes away. Because tension has to be a consistent force throughout the whole string, if we don't have both sides holding up their end of the bargain, nothing happens. A very short amount, because it was moving, meaning inertia is telling it to keep moving. But just because the tension force goes away, if it's still moving, the frictional force still exists. Remember that the problem that we did yesterday, right, with passing the salt, right, that in the case of this here, the tension force is playing the same role as the applied force or the person's initial push. That frictional force would exist until it stopped moving. So does it stop right away? No. There has to be a negative acceleration to get it to zero, but in this case, the frictional force is big enough and the initial velocity or how fast it was going was small enough that the acceleration caused it to go to zero almost instantaneously. But there has to be some slowing down process before it stops. All right, good there. Okay, Krista, now we'll handle where we're going next, okay? All right, so let's go here. And now I'm going to do a different trial, okay? I'm going to add 2 more heavy blocks for a total of 4. That's heavy. All right. And I'll save this run and start a new one up. All right. So we start off 0. And initially, I'm going to apply a small force. I think you can see that the graph goes up, yes, okay? But if you're looking at the block, what's happening? Or not happening? Nothing's happening, right? The block doesn't move, okay? Tension got released back down to 0, okay? So this time, I'm going to pull a little bit harder, okay? Force is going up again, right? But still no motion, okay? All right, last time. I'm going to keep pulling until I get it to move, okay? Ready? Here we go. So, pretty proud of myself on that one. Okay, so 3 sections, right? Differences in motion in all 3 sections, though, right? Remember, this is technically measuring applied force, but if we're in equilibrium, the applied force is matching the frictional force. The first 2, zoom you guys in here. Let me do this real quick. So the first two sections, you can see that I'm gradually increasing the force, right? Those force values are gradually increasing through here. However, no motion occurred. Meaning, if no motion is happening, that block's in equilibrium, net force has to be 0. Same thing is true during the second section. Applied a little more force because I'm farther up on the y-axis, and increased while I was applying the force, but still nothing happens. The last section, increase, 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 increase to a peak value right here, but then we see a drop off, and then during this section right here, fairly constant. While you can't see it on the video, right? You guys saw in the demonstration, I pulled, it started moving, and then I continued applying a force and moved it at a constant velocity across the table. Okay? This section right through here is just what we talked about last time. That's kinetic friction, because the object was moving. But today, we want to focus on this section, and specifically, nope. And specifically, come on. Oh, wrong way. Oh. Come on. There we go. That point right there. Okay? So, those examples are, those demonstrations right there are our first examples of, you guys need unzoom. Those are our first examples of static friction. Static friction acts to prevent motion from starting. The first two demonstrations that I did, pull on the block, nothing happens. We know from previous sections in this chapter that means that net force has to be 0. I am applying a force to this block to your left, right? And if I'm applying a force to the left, it's not your left, right? You give me a look, but that's not the left, but your left. If I'm applying a force to the left and nothing happens, what has to be true? Well, let's go more generally. If I'm applying a force to the left and nothing happens, there's another force equal to that force pointing right, so that we end up with net force equal to 0. There is no other tension force on this object, right, pulling in the other direction. The only force is coming from the table. That contact between the surfaces, that makes it a friction force. Specifically, static friction is the force that opposes the sliding of one non-moving surface past another. Okay? We can have friction even if there isn't motion. Yeah, there's no motion. Totally no motion here. So, okay? That's going to sound good on you. That's going to sound good on the recording. So, even if there is no movement or motion, okay? None of it. Right? Static friction. Okay? We said that kinetic friction opposes motion. There is no motion here for that friction to oppose, but it's got to go against something. So in this case, static friction doesn't oppose motion, it opposes another force, a force that is trying to move or accelerate the object. These pictures illustrate the examples that I was just showing you. First, there can be no static friction. Right now, as that block sits here, it is not moving, meaning that the net force has to be 0. But does that mean there's static friction acting on Is there tension in the rope right now? No, meaning there is no force to your left. If there was no tension force, but static friction still existed, what would the block do? Right? It would go the other way. Static friction has to oppose something. If there's no tension in the rope, there is no static friction, because there's nothing for it to oppose. But if we apply a force to the object and it doesn't move, there has to be a frictional force in the other direction. How big? Exactly the same, so that the net force is 0. As you can see from these examples, I gradually was increasing the force through there, and there was still nothing happening, meaning the entire time the net force had to be 0. If I'm applying more force, but net force is remaining 0, what has to be happening to the frictional force? It has to increase as well. Static friction is not a constant force. It has the ability to change and match an opposing applied force. To a limit, though. If static friction could adjust itself to match any applied force that I applied to an object, what would we see? Nothing would ever move, right? But that's clearly not the case. Some things are harder to move than others because they have a greater static friction value. Going back to, and we'll get into, we'll get back to something. You gave me that look, like, not so. But this value way up at the top up here, that's the value that we're interested in. We refer to that peak value as the maximum static friction. Okay? That's the value we are most interested in, because if we apply a force greater than the maximum static friction, it can no longer match our applied force, and now we have force greater in one direction than the other direction. And if we have force greater in one direction than the other direction, what happens? It starts moving. It accelerates, right? Okay. That happens. Yes. Okay. An atomic level with static friction is, going back to our example from before, if somebody is standing still in front of you and you grab them, that's a lot easier to hold on to them than it is to try and grab somebody on their way by. You know what I'm saying? At an atomic level, just like we talked about with the stopping, those subatomic particles have arranged themselves in the least objectionable position, right? They want to repel each other, and they've adjusted themselves so that they are repelling each other, and they've all settled into a spot. They don't want to move from that spot, right? So if you try to move the one set of subatomic particles, it goes, no, we're gonna stay right here, because if I go here, I get closer to that electron, and I don't want that, right? So that's where static friction comes from at an atomic level. It's still an attraction-repulsion between subatomic particles, but if they're stationary, they will tend to hold on to that position longer, because it moving means that they have to get into a high energy position, or if we refer to it in regular people terms, like a objectionable position, right? Right, go ahead. Yep. That is a frictional force that exists between your head and the balloon, or your hair and the balloon. But that frictional force does have the ability to accelerate things like electrons. And we end up with an imbalance of protons and electrons within the balloon and within your head, and that causes those objects to have charge. When we get past mechanics, we'll get into electricity and magnetism a little more, and how much force exists between those charged particles. So it is a frictional force, but that frictional force has caused then electrons to be imbalanced from protons, and that causes a different kind of force that exists between those two objects.
So you can use friction to...
But we can use friction to create motion, right? If we move those particles from one object to another, now they become imbalanced. Okay? Yeah.
So the reason weight determines how much maximum static friction there is because it's multiplied by motor force, which is times by weight.
So let's do this demonstration, okay? All right, so we'll save this one, okay? And we'll go to run 5. Okay. All right, so I've taken 2 of the black boxes, or 2 of the black weights off of this block, right? So now there's less mass, which means less weight, which means less normal force, okay? All right, so, right, first, no motion, right? Still no motion, okay? And then the last one, okay? All right. So there's that. Let's put on all runs. Okay. So it's totally like looking at Cedar Point from the parking lot. So and the blue is even the blue streak. There you go. So, purple's definitely well. I guess purple could be the dragster. I guess So yeah, purple. It's got an up and down kind of thing. So all right. But more importantly, okay, purple represents the block with all 4 heavyweights on it. Orange represents the block with only 2 of the heavyweights on it. Right? Still the same pattern. Right? A peak and then a drop. This orange peak right here actually came because I got caught again on the table, and so I had to pull a little bit harder, right? But this peak much lower than this peak. So again, Luke, we see that what's affecting the frictional force that exists between those 2 objects? The normal force. And, oh, look at that equation. Okay. So, Brett, hold on a second. Let me finish this up here. All right. So, another coefficient of friction, but this time the coefficient of static friction. And you'll see here that the left-hand side of this equation gives us a way to figure out the maximum force of static friction. That's the important one, because we need to know what the maximum static friction force is in order to overcome that maximum friction force, which causes an imbalance. Now we're not in equilibrium, now we accelerate. Okay? So, underneath maximum static friction, there are the first sentence that shows up here, there are 2 things that we need to change about that sentence. I don't like what your book did here. There are 2 words that I would like to change in that sentence. Any ideas? So it says a stationary object begins to move when the applied force equals the maximum force of static friction. There are 2 things I would like to change about that sentence. If the applied force equals the maximum static friction force, what's true? It's still in equilibrium, right? It's still net force 0. So let's change equals to exceeds. Okay? Then there's one more word I'd like to change. You could argue that it's okay, but there's one word that I would like to change and make a little different. Anybody? Any ideas? Before it experiences kinetic friction, it has to, I heard it, right? Or it could move but not be accelerated, right? But in this case here, in order to start motion, beginning to move is acceleration. So you could kind of say that that's kind of saying the same thing, but I kind of like this a little better. So, all right, good there. Okay. Acceleration is a change in motion, right? Yeah, yeah. No. All right. Guided example 5.12. Stranger than friction. This chapter is full of zingers. There's a couple of humdingers there. So, all right. So it says students in a physics lab design an experiment to determine the coefficient of static friction between a 1.8 kilogram jack-o'-lantern and the tabletop on which it rests. Their setup is shown in the figure below. The basic procedure is to pour sand slowly into the pail until the pumpkin begins to slide. Apparently they don't have force sensors in their room. I don't know, but yeah. It says the pail with the sand is then placed on a scale and it is found to weigh 11 newtons. What is the coefficient of static friction between the jack-o'-lantern and the table? My guess is the person that wrote this book thought that this lesson, this chapter, would probably fall in around Halloween, and so they would throw this jack-o'-lantern problem in. We're a couple weeks late, but, you know, so. What? If you were trying to get through the whole book, you know? Yeah, so. True. True. All right, let's go through the process, right? First thing we do, so we still use that Greek letter mu to represent the coefficient of friction, but this time we want to find the coefficient of static friction. Now, just to clarify a little bit, right, the previous slide and on your previous page in your packet, in order for us to figure out the coefficient of static friction, we really have to know two things. What do we have to know to figure out the coefficient of static friction? We have to know normal force. We also have to know what is the maximum static friction value. Those are the two terms that show up in this equation that relates the force of static friction maximum to the normal force, right? We need to solve this equation for coefficient of friction, so we need to know those two things, okay? All right, let's go here now, right? Two other things that we know in here. The mass of the jack-o'-lantern is 1.8 kilograms, and the pail with the sand weighs 11 newtons. We said that weight is our term to represent what? What is the weight of an object? Gravity. Specifically it's the force of gravity. Good. So weight of the sand is 11 newtons. Okay? What we're looking for, what we know, free body diagram. Okay? Let's start with the jack-o'-lantern. First force we can put on our jack-o'-lantern free body diagram. Okay? Caitlin, you just told us that to find the weight of something, what do we do? Mass times the acceleration of gravity, right? 9.81. And if I remember correctly, pretty sure 17.66 newtons. that good? Okay. All right, so that's the first force. Second force we can put on our jack-o'-lantern. What do we call that? What's that N force? Normal force, right? Say again? Not really, no. All right, so this is our normal force. That's true. Well, yes. Unless we're talking about the force, right? Then that might be unnatural. So. Something like that. Unless it goes sideways, then it's more applied force, you know. All right. What does normal force have to be in this picture? Normal force has to be 17.66, right? So, we're halfway there, okay? All right. There is a string attached to this jack-o'-lantern. Strings apply what kind of forces? Tension forces, right? So there's a tension force going in this direction. Here's where we have to sort of not be false about things or make stuff up, but we have to kind of massage the details a little bit, okay? Up until the point when this jack-o'-lantern starts moving, what else has to be there? If we put sand in this pail and nothing happens, the jack-o'-lantern doesn't move, there is a static friction force. And if the jack-o'-lantern isn't moving, how big does that static friction force have to be? The same as the tension force. If it was bigger than the tension force, what would happen? It would move backwards, right? And that doesn't happen, okay? There has to be something in the pail in order for there to be a tension force. So, the kids keep putting in sand, right? Keep putting in sand, keep putting in sand. And let's say they were so good about it that they put sand in and it didn't move. They knew they were getting close, and so they put one extra grain of sand in, and then it budged just a little bit. Okay? So, it told us in the problem that at that point, when they took the bucket of sand and put it on the balance, we came up with a weight of 11 newtons. Tension transfers force all the way through. So if 11 newtons of gravity is pulling on this pail, guess what's happening to our jack-o'-lantern? It's going to feel a force of 11 newtons, because that's what tension does. It's the same on both ends. Okay? Now, here's where we have to kind of go, okay. We're talking about the difference in 1 grain of sand. Yes? Okay? Meaning that if there's 11 newtons plus 1 grain of sand, that's bigger than the static friction force to cause acceleration. So in this case, we can say, all right, we know that this really can't be the case, but if 11 newtons plus 1 grain of sand cause motion this way, we're going to go with 11 newtons as the maximum static friction force. Does that make sense? Even though we know that can't really be true, right? We're talking about the difference of 1 grain of sand. Now, yes, although Simran, if they gave you 11.5, right, they still have to tell you that that's when the jack-o'-lantern first started to move, right? Because if we had a tension of 12, right, it would start to move, but it would also accelerate as it was moving, right? We need that spot when it just starts to move. Does that make sense? That, yeah, for our purposes, we're just going to stick with that, right? If it says, you know, we got this 11 newtons, right? Now, if this is a multiple choice question, the best answer would be the tension has to be greater than 11 newtons, okay? But for our purposes here, we're going to be good, okay? That gives us the maximum static friction force, Now we got the two things that we need, and if I'm not mistaken, I believe it comes out to be 0.62. Okay. Good there? Technically, there is some friction there, but that makes that problem a lot harder. Okay, so we're going to say this is like a perfect pulley with no friction, which it's not in real life, but that makes the problem a lot harder if we don't do that. Okay, all right, good there? Good job today, everybody. Have a good weekend. Like I said, Monday we'll probably do our review activity movie. Tuesday I'll give you time in class to study, test. Monday and Tuesday when we get back from break. Okay? Yes, there is homework online, Krista. Yeah. So, and the answers are posted. So, okay. Oh. Luke will take them for after practice.
This is before practice. I need to win one good after that.
All right, have a good weekend, everybody.